bringing up our last presentation for the day, Federico.
Hello, do you see my screen?
Indeed, I see your screen.
Okay, so I can go. I don't see you.
You don't see me.
Yeah, it's fine, but I see that I'm sharing, but
well, let's see. I can hear you. I can.
Okay, I can go.
Yeah.
Well, anyway.
Yep.
Okay. So hi everyone. I'm Federico Vincentelli. I will present some results I obtained the last few years using X-rays and fast infrared photometry on black holes and neutron stars, because we do not all ignore neutron stars, as it was stated at the beginning of the session. So as Alex and Andre described very well earlier, we all know that in X-ray binaries, the X-rays are dominated by the accretion flow and the radius is generated by the jet, but we still don't know a lot of details of these two components. And optical and infrared emission, and especially the variable emission, can give us information on these two components to try to understand the details, because there are in fact two main scenarios that can explain the optical and infrared emission. And the more historical one that explains the optical infrared emission as optically thin emission from the jet, or there are also models which manage to explain the optical infrared variable emission as synchrotron radiation from the external regions of the hot inflow. And so what we do is to try to do simultaneous high time resolution observations in X-rays and optical and infrared to try to measure the connection between these two components and this entanglement between these two scenarios. So the main two observables are, for example, in the time domain, cross correlation function, which can give us, for example, the delay between the X-rays and the optical. And for instance, this is the 0.1 second lag famous by Porshak-Gandhi in V404. But another method to, before going on, you can already see that there are complex shapes. That's telling us that there's indeed more than one component. And this is even more clear when we go in the Fourier domain. This is the time lag shown by John Pace for Max 1820, not the 4, where you see two clear components at low frequency and high frequency. But you can also, for example, study the power spectrum of optical and infrared, and for example, measure QPOs and lag delays between with the X-rays. So the two main scenarios have main features that are explained better some of these observables. For instance, the jet scenario explains optical infrared radiation as shocks inside the jet. And this naturally explains the 0.1 second lag as the travel time from the inflow to the outflow. And on the other hand, the hot inflow model explains very well anti-correlated cross-correlation functions, because optical radiation is gained by the synchrotron emission, while the X-rays is synchrotron same Compton, and so from the same population of electrons. And therefore, the anti-correlation is naturally included in this model. And the other good thing of the hot inflow model is that it has quantitative predictions for the QPO that are still missing for the jet model. So given these two scenarios, we can go and now explain I can now go and show you the main results I obtained in the last 2 years. This is a Star Project CTI-4, where we managed to do the first infrared monitoring and X-ray monitoring during the decay with fast variability. And we managed to obtain only one strictly simultaneous observation at the peak of the outburst. And you can see this is in fact the time lag as a function of the Fourier frequency. There is the 0.1 second lag that has been already observed many times for this source, but there is also a negative phase lag, which is quite still unclear, because it can be explained both with hot inflow and jet model. I don't have time to go into the details. We can discuss about it later if you want. Regarding the XTP, I wanted just to show you what we can do now, because this is this is so it would be nice to do an energy-dependent study of these lags and, for example, the coherence to try to extract which physical component of the inflow is connected to the outflow. But as you can see with XMM, already with all these three beams, we cannot see a very big difference in the lags as a function of energy. So EXTP, given it's significantly larger effective area, can certainly help on these regards. The other thing that we did is that I think is the main result of this paper is that we managed to track the components of the power spectrum as a function of time, and we managed to see that on one hand that there is an infrared QPO that changes as a function of time and follows the X-rays. So this is a further constraint to QPO models. But mainly, we find that the infrared power spectrum shows always the same damping frequency. This means that there is some mechanism that filters out the infrared variability that is from the jet at high frequencies, because there's the 0.1 second lag. And therefore, this can set as also Alex said before, a typical dimension of the jet, and in particular of the jet launching radius, because we can connect this time scale, this frequency, to the viscous time scale that generates the input variability, and we managed to obtain a constraint of 10 Rg for the XSM-4, and this and therefore the launching radius should be constant at 10 Rg during the whole rebrightening. So then we have another source. Then apart from that, I have another source to show, Maxi 1535, that was a very bright source that went into outburst in 2017. We observed with XMM and with XMM and Hawkeye, so the fast infrared photometer, and also with time resolved mid-infrared observations, as you can see in magenta. And this is the first time that this kind of observation were done, and this was done through SmartNet, that is say a website to try and coordinate multivariate observations. If you don't have it, I suggest to sign up. It's totally free. There is no collaboration. There's anything. So it's just to help astronomers to coordinate. Anyway, apart from that, we did the cross-correlation functions between X-rays and infrared. As you can see here, it has a very complex shape. It doesn't have a 0.1 second lag, and it has an anti-correlation. And as I said before, this can be explained from both jet or hot inflow, but it needs more detailed modeling that I didn't do for now, but still work is in progress. The big result, however, of this paper is doing the Fourier domain techniques, applying the Fourier domain techniques, because we managed to measure for the first time QPO at the same frequency in X-rays and in infrared. And looking at the phase lag, you can see that they are also in phase with a 0 lag. And this is highly constraining for models, for the two models that try to explain the optical and infrared variability. For instance, if we try to obtain such a phase lag for the hot inflow model, we have to have a inclination of 50 degrees and a truncation radius of 30 degrees, of 50 Rg, which is a bit big because we are close to the transition, but it's consistent with what we find with X-ray spectral speed. On the other hand, if you apply a simple causal relation for the jet, so you just use the upper limit of the time lag between X-rays and infrared, you can constrain the jet model, and you obtain, on the other hand, a declination lower than 40 degrees and with a gamma higher than 1.7. And so this is the interesting thing is that there is actually a discrepancy between the two models, and I think this might suggest that there is an misalignment between disk and jet, but we can discuss it further. Last thing I want to show is about a neutron star, because as you can see, we find very interesting results on jets and black holes, and we are trying to also find them in neutron stars. We didn't find it. We didn't find fast infrared variability from a jet yet, but in the meantime, we managed to observe the infrared counterpart of an X-ray burst of for the famous X-ray burst for U1728-34, and this can be highly constraining for the orbital period, because if you assume that the source is in antiphase when this happened, then we can put a lower limit to the orbital period, and this has to be, in this case, higher than let's say a few hours for let's say a reasonable inclination, and therefore, this value is way higher than what was believed, because this was believed to be a ultra compact source. So this shows also the power of fast multivariate variability also for network studies, and not only jets but also to map the accretion flow, and this is certainly an interesting case for EXTP. For last slide, for the future, I want to just show the prospect for this kind of studies. So XTP will be launched in 2027. In the future instruments after Hawkeye will not have fast infrared photometry. At least this is what is stated on their webpage. In theory, the next instrument after Hawkeye, that's the fast infrared photometer that I'm using, should come in at VLT in 2027. So usually there is one period of commissioning and more instruments can be together at the VLT. So I guess probably 1 year of overlap between Hawkeye and EXTP will be, there will be at least probably 1 year overlap, let's say. But so this is for the infrared side. However, for the optical side, a lot of fast photometers are being built in Italy, but also in the US, so in South America. So certainly there is hope for optical. As Tom said before, it's a bit messier in optical because you have more contribution from the hot inflow or from the disk, but still you can study jets. On the other hand, JWST also can do fast photometry, but as also Tom said, the timing accuracy has to be tested. So I'll leave you here for the conclusions, and thank you very much.
Thank you, Federico. Appreciate it. So we can entertain a few questions for Federico, given the time. Mariano, your hand is up. Is that from the last time, or is that a new hand up?
It was from last time, sorry.
Okay. Fair enough.
I was expecting a question from Mariano, but okay.
Yeah, that's right.
Sorry, Federico. No, we can talk in private.
Looks like Dimos has a question. Is that right? I see a hand up. Let's see. I see Kazanas actually has his hand up. Apparently, but that must be also from maybe last time.
Yeah.
No, he can type the question to the question and answer. I think he doesn't have the talking permission at the moment.
Can you unmute me? Yeah, it has.
Yeah, so he needs to be. Yeah, so now he has.
All right.
Okay, there you go.
Okay, thank you. Is there any lag between the X-rays and the infrared? I mean, this is kind of interesting. I look at the power spec that you have,
but which?
Oh, I forget now which.
This one.
Yeah, this one.
Oh, the lag is 0.
Yes, there's a break in the power spectrum here in the X-rays, which is at some frequency.
Yeah.
But the infrared has a similar power spectrum, but the break is a factor of 10 lower
yes.
time scale. Now,
the QPO, this extra component here.
I think there is something going on in the infrared also.
Yes.
It's not like a QPO, but there's some feature there.
It's 2 sigma detection there, but if you look at the phase lag, it is quite clear that.
Is there, which one leads which? They're simultaneous?
They are simultaneous. They have a 0 phase lag.
Okay, I have to think about it. Then the infrared has longer delay timescales, basically. That's basically it. That's the only thing I can think of here. I mean, the characteristic timescales are off by a factor of 10. Well, if they're simultaneous and they go together up and down, or they don't.
Well, the upper limit of the phase lag of the time lag is 0.04 seconds.
Do you mind if I interrupt a minute, Federico? I think Demos is asking you about the phase lag in the whole power spectrum, not just on the QPOs, but you're answering just
right. I'm talking about
right?
the whole power spectrum. Yes, that's right.
Sorry. The whole power spectrum. So at low frequencies, there is the infrared seems to be leading, but it has a negative phase lag.
It has negative, of course. So that's nice, because we expect that something comes from low frequencies and ends up with high frequencies. So this will be an example of this situation. And now I can see now you have the power spectrum, and the power spectrum has a break, if you like, in the X-rays, which is a factor of 10 high frequency. So things must be happening much slower in the infrared, I suppose. That's this is nice data, because I haven't seen anywhere situation we have the power spectra and the X-rays, and at the same time in some low frequency other than X-rays. So that's I have to think about it. But this is an interesting data. Thank you.
Okay.
Somebody else may have some ideas. I'd like to hear it.
Yep. Anybody else?
Can you share your presentation again?
Yeah.
So can we say here that, the infrared is leading in the lag? Because, when I look at the coherence,
this is the cross correlation function.
Okay, so by just technique. So how did you calculate the cross correlation? By just taking the whole light curve, or just you pick the
whole light curve?
By taking the whole light curve, right?
Yes.
Okay, thank you.
Okay.
But this cross correlation function, if you have an anti-correlation, that's the reason why you get a negative phase lag. Just if you have this kind of cross correlation, then the phase lag here is expected, even though there is some nonlinear process because the coherence is low.
Yeah, so when I look at this, so first, up to like 0.3, 0.4, looks like there's a kind of leading negative phase lag.
Yeah.
But not the overall picture. Anyway, thank you.
The fact that the coherence level is fairly low, does that mean how significant is that?
The
noise probably, right?
No, the noise. This is intrinsic coherence. The noise has been subtracted. It means probably that the process that is governing the relation between X-rays and infrared is intrinsically nonlinear or incoherent, let's say.
Yeah. Okay. Well, thank you, Federico.